Thank you very much, and a very nice afternoon to all of you. I'm very happy to be here at SEMICON this year, and I'm looking forward to give you a brief overview of how Infineon sees especially the topic of gallium nitride and how it can contribute in the mission that we have at Infineon, which is digitalization and decarbonization. So in my talk, I want to briefly go over Infineon at a glance. I will keep this very, very short, to immediately then go more into the gallium nitride topic itself and how gallium nitride especially can help to power AI. We all know AI is the hottest topic right now in the market, and with gallium nitride actually we can make huge advancements in delivering the power to these power-hungry applications. So, as already said, Infineon is a big player in the power semiconductor industry. You see here we have a very strong market position in the automotive market, in power itself, but also in the microcontroller market. Our position is pretty strong. At this point in time, we believe we're number 2 in the microcontroller market. And when we look a little bit deeper, we can see that we have a very strong market position at Infineon for power discrete, so this means mainly MOSFETs and IGBTs like that, but also for power ICs. And that is really important that power ICs go together with power discretes, because as we move from silicon more to wide bandgap based systems, like gallium nitride based systems or silicon carbide based systems, it's getting increasingly important to deliver the right system solutions. And right system solutions means we need to have not just a power switch, like a GaN switch or a silicon carbide switch, but typically those switches also need very dedicated driver ICs, especially when it comes to gallium nitride. And then, because you want to extract the full value of GaN, often you also need new controller ICs because topologies change. And when topologies change, you need controllers modified, you need drivers modified, you need new software, algorithms, and everything. And that is why application understanding, system solutions are much more important now when we move from silicon, especially to gallium nitride-based systems. And that is one of the major focus areas of the Infineon GaN strategy also. Why is GaN a great semiconductor material? I don't think I need to tell you. There's a lot of value it can provide. Yeah, we see on these examples here, on the charger that you see here, 65 watt, that it's simply getting much smaller, at least by a factor of 2. Also the adapter that you see here on this slide is getting much smaller when you use gallium nitride instead of a silicon or silicon carbide switch. These are applications where I think we all know already GaN finds its adoption, but there's more applications like you see here on the bottom, e-bike motor drive applications, where with gallium nitride you can shrink the design substantially and increase the power level for the e-bike inverter. And server power supplies, and I'll talk about this in more detail later, also here gallium nitride can help to deliver more power in the same form factor. So it's smaller size, it's often lighter weight, because gallium nitride delivers lower power losses. That also can lead to lower system cost, and eventually, of course, that reduces CO2 emissions and helps in the mission of decarbonization. Because of all these benefits, we see the gallium nitride market growing. So here you have a chart that is actually taken from Yole, and the latest update of the GaN market growth is actually this dark blue one. And there you can see that in this year, the gallium nitride market roughly, so I need to do it like that, so 2024 was around $500 million. But you can also see that the market is growing quickly, a CAGR of 50%, and it should reach in 2028 around $2 billion, because GaN delivers all those benefits. So it's a very fast growth of this market. You can see also on the right-hand side again, we believe GaN is really a revolution. Often in silicon and silicon carbide-based systems, you use what we could call a two-stage conversion. You have, for example, in a solar microinverter, a DC input, a DC-DC stage, and then you convert this into AC to feed back into the net. But with GaN, because it has unique properties, like bidirectional switch capability, you can do this in a single stage. That leads, again, to smaller size, higher efficiency, lower system cost, so a lot of benefits. But, as you can see here, the system changes. New topology, new controllers, new gate drivers, so the entire ecosystem needs to be developed to make sure the GaN can be really adopted. Now at Infineon, we are very committed to that. That's why we acquired GaN systems last year. With that, we have a huge patent portfolio on the GaN-based technology itself. We formed a very big GaN team now at Infineon. We are around 450 people in this business line. And of course, in operations, another couple of hundred people, actually, that are all working on gallium nitride. So I believe we're around 1,000 people that are really focused on bringing this gallium nitride technology forward and bringing it into the market. And as said, the third point here, which is very important, is this application understanding, right? Because the system changes so much. If we want to bring GaN successfully into all these applications, we need to have very strong application understanding. Having all of that, the R&D and the IP is all great, but then we also need to manufacture. And so here we believe, because the market is growing so fast, we need our in-house capacity. So we're building up our 8-inch in-house capacity for gallium nitride. And in addition, we need to have foundry partners. The market is growing so fast that it will be sooner or later a challenge to just do this all out of in-house capacity alone. So therefore, combining both foundry path and in-house manufacturing path is really a focus that we have at this point in time. As said, with GaN, you can do amazing things. You can do the standard transistors as we know them. So this then is similar to the switches that we know out of the silicon market or space. But then you can also realize so-called bidirectional switches. So you can put into one die what normally is two back-to-back silicon switches into one actual gallium nitride-based switch. And that is a unique capability that gallium nitride actually delivers. And in certain topologies, like Vienna rectifiers or matrix inverters, this is really a huge benefit because it increases efficiency, it reduces system cost, and it provides all the benefits of gallium nitride. Gallium nitride is also a lateral technology, as you might know. So current flow is not vertically through the device, but laterally on the surface of the device. And that makes it much easier now to integrate features like current sense in a gallium nitride switch like here. So here we simply add a current sense. And with that, you can replace shunt resistors that are typically used in a system and reduce system cost, increase system efficiency again. And this is not where it stops. Of course, you can also co-package with ICs like gate drivers. Often customers are concerned about the gate drive circuitry when it comes to gallium nitride. And then we can simply co-package this together with the gate driver ICs that we also have at Infineon. And as I said, often topology changes. That means controllers need to change. So therefore, dedicated controller ICs also need to be developed. For example, totem pole BFC controllers or existing topologies just going to much higher frequencies, 500 kilohertz and megahertz for an LLC converter, for example. So these are all products that need to be established in order to really facilitate the transition to gallium nitride and bring these system solutions into the market that you saw on the previous pages. Now, how do we see this transition then happening along a couple of applications? And let me give you some examples. So the way you can read these charts is when this year is 2020 and you see an ocean color, the majority of the designs was done with silicon. And if you see a berry color, we believe the majority of the designs will be clearly done with gallium nitride. And if you see an orange color, then it would be silicon carbide. Now for chargers, high voltage switches, when you think 4 or 5 years back, there was not so many GaN-based chargers around. When you now look into the market, it feels already like the majority of the chargers is based on gallium nitride, so this transition is happening, and actually already today, we can see from our customers, the majority of customers use a high voltage GaN device in their charger designs. On the Syncrack side, So the low voltage, 100 volt, 80 volt, 40 volt devices, this transition is not there yet. Silicon is extremely well performing on the low voltage side and medium voltage side, and the controllers are not optimized yet, so the dead times in the control loop are simply too long still to use gallium nitride. As these new controllers come into the market and GaN technology improves further, we believe that also here we will have gallium nitride in the majority of the designs, probably in 3 to 4 years from now, also on the low voltage and medium voltage side. And then we will have full GaN-based chargers and adapters in our pockets. Server power supply, I'll talk a little bit later. Onboard chargers, very interesting topic. Until recently, the majority of designs were really based on silicon, and pretty much the majority that is driving on the street is using silicon devices today for onboard chargers from 6 kilowatt up to 22 kilowatt. The designs that are happening now and starting to ramp are largely based on silicon carbide, but you can also see that the third wave will come, which is gallium nitride. We see that many customers, OEMs and tier ones, they are very interested in gallium nitride for onboard chargers. With GaN, you can double the power density of an onboard charger from 3 kilowatt per liter to 6 kilowatt per liter by moving from silicon carbide to GaN. So very likely, end of next year, beginning 2026, we will see the first onboard chargers in higher volume on the road with gallium nitride. Then some other applications, motor control, like motors in white goods or also battery-powered motors. This would be here the DC-DC, HV here is the AC-powered motors. Here frequencies are typically lower, 10, 20, 40 kilohertz. Gallium nitride does not shine yet, but there are customers who, for example, based on FOC-based designs, increasing carrier frequency also can extract value of gallium nitride there. Also motor designs would need to change. So a lot still needs to happen on the motor control side, but we see also here gallium nitride can provide value. And last but not least, residential solar, or so-called microinverters. So what we see here is that clearly there is benefit of gallium nitride. It started actually with silicon carbide transition, already slowly happening, but with the bidirectional switch in specific topology configurations, we will see also gallium nitride in microinverters. And this will happen actually faster than shown here. Definitely next year there will be microinverters on the market that use gallium nitride in very high volume. So this should show you not all the applications that we're addressing at Infineon, but just a couple and how this transition will happen. But when you look at 2030, pretty much everywhere you see a berry color. So pretty much everywhere we believe the majority will be actually gallium nitride. And that is why it's so important for us to move this technology forward and develop the entire ecosystem for gallium nitride. Now let's talk a little bit more about how GaN can help to actually power artificial intelligence solution or AI systems. I think you're all aware that standard server CPUs, they are in this range of 250 to 500 watt power consumption, and the standard server switch mode power supply needs 800 watt to 1.2 kilowatt capability roughly. AI systems totally different. As you can see here, today we already talk about 700, 800 watt, very soon 1 kilowatt power consumption, further really exploding into 2 kilowatt power consumption. Meaning such a power supply now needs 3, 5 kilowatt, 8 kilowatt, 12 kilowatt capability, very high efficient at very high power density. And of course now, all of that really sounds like this must be the right spot for a right band gap for gallium nitride. What we find today is, as we move up this power demand levels, that at this point in time, combining actually silicon and silicon carbide and gallium nitride is really the best that we can do to optimize performance and still keep cost low. So why is that? I will skip over this slide. It's just a brief overview of the various technologies. Why is that? So best explained with the so-called PFC stage. So in every power supply, you have first a PFC stage and then a DC-DC stage. So on the PFC stage, so somewhere here your AC input comes in, and then you go first to a 400 volt intermediate bus voltage. And the traditional approach is what you see here. You use silicon in a classic CCM PFC. It's fairly reliable, it's easy to design in, it's very well known. Efficiency level is about 98.5% peak efficiency. And the total system can reach a density of around 50 watt per cubic inch. That is not enough for an AI system. You need to deliver more power in the same form factor as we've seen before, at least double. So we need to double the power density. That means first step is to change the topology to a so-called totem pole BFC as you see it here. And where needed, use actually wide bandgap. So the first step would be to go to this totem pole BFC, so-called CCM totem pole BFC, and use, for example, silicon carbide here in this fast switching leg. And there's always a so-called slow switching leg that only moves with 50 Hertz. Silicon is by far good enough to switch at 50 Hertz. It's still the cheapest technology. So combining in this way gives you actually the ideal cost and a significant efficiency and a performance improvement. But if you need to push it really even further, right, if you need to go to 120 watt per cubic inch, which we eventually have to do, then there is no way out, you must go with gallium nitride. Otherwise, we cannot power such systems anymore. The power, the space that is available to power them is just not enough. The way this is trending is that a single rack will very soon require a full megawatt of power. That means this does not work at all. So we must go to what you see here on the very left-hand side, what means you must go to gallium nitride. Otherwise, you will not be able to deliver such a power solution for the PFC. Same we see for the so-called DC-DC stage that's coming then after the PFC. You have two choices essentially, a so-called phase shift full bridge or a LLC. And really LLC is what is now really being adopted wide in the market because as you can see, efficiency goes up and power density also goes up significantly. So in order to go to this very high power density requirements that we need to fulfill, we need to go to such a LLC topology. We need to push frequency up to shrink the passive components and further gain space. And that again means using gallium nitride. Here it's the high voltage switch, and here on the secondary side, it is the 100 volt, 80 volt switch typically. If the switching frequency is slightly below 500 kilohertz, you still can do silicon, but eventually also here, we believe you need to work with gallium nitride. Bringing this all together, you can see here how we believe this AI power supply evolution is looking like. Today, very often 3.3 kilowatt solutions or 8 kilowatt solutions. Remember, a standard server only needs around 1 kilowatt. Right? So an AI system needs much more power delivery capability at very high efficiency levels and very high power density levels. And we combine typically now the material systems to really extract the biggest value and the maximum value and fulfill these demanding requirements of such applications. Eventually, we are also working on a 12 kilowatt design that will be available beginning of next year also, where we push it even further to 12 kilowatt, because we see from our customers even 8 kilowatt is not enough. We need to go even to higher power levels. So a big impact AI has on power delivery solutions, and you can also turn it around. Without the right power delivery solutions, AI will also not work. So this is really a must, having right bandgap, having the right topologies and controllers and gate drivers in order to be able to power AI. And that already brings me to the summary. I hope I was able to show you that we have a full range of power technologies in Infineon, and especially that gallium nitride, at the bottom, that's the most important statement, will take over a wide range of applications, from the consumer space, charger adapters, to the more industrial space, like these AI servers, towards the automotive space, like onboard chargers. 4 or 5 years ago, GaN was hardly visible in the market. Today, it's very visible in the market, and in 5 years, I'm sure most of us will drive an electric car with a GaN-based onboard charger. Thank you very much for your attention and looking forward to some questions.
Okay, so now open questions from the floor.
Thank you for your presentation. I come from Semi and Analysis. I want to ask you about, because you just say for the AI server, right? So you just say maybe combine the silicon carbide, silicon, and also the GaN nitride. But you just show the silicon combined for silicon carbide or silicon combined GaN nitride. How about the silicon carbide combined and GaN nitride? I just want to know, because I just think about maybe the efficiency would be much higher than silicon carbide and silicon. Can you just say, explain about this?
Yeah, so if I go back, so on the silicon carbide, oh, it's not visible anymore, doesn't matter. Silicon carbide and, oh, thank you. I think it was here, for example here, right? So in this kind of topologies, you always have here these switches moving with pretty high switching frequency, around 100 to 200 kilohertz, and they only do 50 hertz. Yeah, so here you need really just a switch. It just needs to be having the right RDS on. Otherwise, switching performance not really relevant at 50 hertz. So therefore, use silicon, the cheapest you can get. That's good enough. But then here you need something that is high performing. 150 kilohertz at these power levels, you can waste a lot, dissipate a lot of heat, and so on and so forth. So therefore, here you could use silicon carbide. So this is where we say, okay, use silicon carbide and silicon. And then in the next stage, then use all gallium nitride. And in this way, you really get the best efficiency. So if you have enough money, then you can still use silicon carbide here, but I would say, why spend it? It's not needed, right? Now the big question is, what is the cost evolution of GaN and silicon carbide versus silicon? Because maybe there is a day where gallium nitride, especially gallium nitride, can get down to silicon cost level. And given how close gallium nitride manufacturing is to silicon manufacturing, I think we can foresee that this day will come somewhere in the future. And then, potentially, it will be all gallium nitride based. Does it answer your question? Good, thanks.
Hi, my question is, apart from gallium nitride and silicon carbide, is Infineon looking at another kind of wide bandgap semiconductor, like diamond or something else that you could share?
Very good question. I think at this point in time where we are really thinking about, so my responsibility is business line, so I really have to generate revenue fast and ideally even faster. Gallium oxide is definitely interesting, and from a pure, let's say, advanced R&D perspective, yes, that is being also looked into, but we are not yet at the point where we will create devices that we want to sell to customers. It's early, right? So we try to understand the properties, how to manufacture them, what are the advantages, and so on and so forth. So it's definitely very interesting, especially the gallium oxide topic. But we are in a, let's say, advanced R&D stage, not yet in a let's generate revenue as fast as possible phase.
Thank you very much for the very interesting sharing. I just wondering that in today's general, everyone talks about how to wide bandgap semiconductor device to help for the AI server. But we come from last year in the STEM forums, everyone talking about how to use wide bandgap for the EV application. But in this year, it seems like nobody talk about EV anymore. So I wonder from industry perspective, do you feel like it's less increased hope that people can use wide bandgap in the EV in the nowadays?
Yeah. Well, I think that's a function of how the markets are behaving, right? So we all know that the EV market is not growing as fast anymore versus expectations, but AI is growing like crazy. So therefore, there's so much focus on AI. That does not change anything to the point of using wide bandgap in EV. right? I think on this page, and here it's just the onboard charger, we see clearly transition away from silicon to wide bandgap. First silicon carbide and then gallium nitride. And traction inverter, very similar, of course, increasingly more silicon carbide used. And we also have already first projects with customers to look into gallium nitride for traction inverter, even main inverter. So for EV, clearly we see continuously interest in wide bandgap, moving to wide bandgap because it helps to extend battery range, which is most of the drive range, which is one of the key features an EV, of course, must have.
Thank you very much.